The following recording is of the MIT PhD professor Kevin Esvelt speaking at the Victoria University of Wellington, New Zealand on the topic of the new CRISPR-Cas9-driven genetic engineering, and more specifically the use of the new gene drive. Kevin and his team are receiving funding from concerned philanthropists and DARPA of the US military to develop both a safe and reliable alternative to the gene drive, known as the DAISY drive or daisy chain drive, and also a so-called reverse gene drive in the event that a rogue state or bioterrorist may attempt to utilize this technology in a harmful way. If you have no idea what I'm talking about, and what any of these words mean, do not worry, he explains most of them in the recording. He is talking in New Zealand because of the unique ecological situation we are in, and because we as a country have sworn to remove all foreign invasive species from our shores. Some more things to note. This was recorded on my friend's cell phone from 15 meters away, so despite my doctoring of the sound, the quality leaves something to be desired, so I apologize for that. Secondly, his microphone spontaneously breaks halfway through, so I will attempt to audio balance this, but I am merely human. Enjoy.
In many cases, they only exist in mathematical models. So this is the earliest stages. This is not typically when one comes to talk about something. But our goal is to do so early because there are many different directions that it can go in. Some of these may be more or less suitable for Aotearoa. Perhaps some of these may have flaws in general that would render their use unwise anywhere. And if you can point that out to us, we would be deeply grateful because we do not wish to see these misused or used unwisely in any way. Now, again, this kind of technology is very different from most because suppose we were developing a new medical treatment. If we did so in a closeted manner, the way most science is done, then it would go through the development process, it would be turned into a product, it would be submitted to regulators. If it were approved, then your doctor could recommend it to you and you could say no. But this is about developing a technology intended to alter the ecosystem. So if it went through that process, and then it were approved, even if it went to a vote, suppose you were to vote against it. If the majority approved, it would be used and you would be affected. You would not be able to opt out. So if this kind of technology is developed in a closeted fashion, as almost all science and technology are, then it denies you a voice in decisions intended to affect you. So that's why we believe that all technologies like this that would have that kind of shared impact must be developed in the open and invite the guidance of the local communities. This is difficult because what we are talking about is biotechnology. And even though the first applications of biotechnology were arguably things like recombinant insulin, but most people don't think of that as genetic engineering. That gets lumped under that's medicine. Instead, when you say genetic engineering, people think GMO crops, or even worse, people think Monsanto. And frankly, there isn't a GMO crop on the market right now that offers the typical person eating it any advantage whatsoever. Not that's noticeable. A little bit cheaper. That's about it. Nothing obvious. So why should we be surprised that people aren't terribly enthused? It doesn't really offer most people anything. So if you're going to develop a new technology, don't do it that way. The corporate profit dominated doesn't actually offer benefits to most people. Ensure that early applications should always offer clear and obvious benefits, either to the people, to the natural world, or to both. Again, discussions of the technology should come before experiments, especially if it's the sort of thing that would have that kind of shared impact. Because again, once you start doing experiments, you're moving down the development path in a particular direction. And that means it could go in a direction that is not actually the wisest way to go. Safeguards should be agreed upon early, especially if it's the kind of technology where it might, if released from the laboratory, replicate and begin to spread. There should always be built in an independent monitoring and assessment process. Because who's the last person you want to test a hypothesis? All the students in this room. Who's the last person you want to test a hypothesis? Who's the single most biased person in the world? The person who proposed it. That's right. Now, never mind that that's how science normally works. That just shows us that science is broken. But the same is true for inventions. No matter how hard we might try, if we're the ones who invented and developed it, we are biased, and we cannot be trusted to assess it for safety or efficacy. You need independent assessment. So that needs to be built in. And overall, we call this sort of new way of doing it by inviting feedback from others at the earliest stages, responsive science, because it is all about creating a dialogue between everyone who would be affected. And make no mistake, the future of our civilization will be determined by the technologies that we invent and the wisdom with which we deploy them, or choose to refrain. So why Aotearoa now? And the answer is, you're the only nation in the world that is committed to remove an invasive species from your shores by a particular date, or actually at all. And so, given that you have committed to remove these rats, the question is, how are you going to go about doing it? And biotechnology is one potential way that you could choose to do that. Or you could choose to go other routes. So the question is, can various forms of gene editing, in particular the forms of technology that we're developing, potentially make New Zealand predator-free? Again, I'm just going to re-emphasize this. Normally, you only come and hear about this once the technology is already developed and working in the lab. Right now, we have not even developed a proof of principle in mice. Deborah, down here, is a PhD student in my group, is currently in the process of making the mice that will be that first proof of principle. But those mice are not intended to actually do anything in the environment. Rather, they're a visual example of how the technology works, because the genetics is written in the colors of their coats. So there isn't anything yet that might actually be used. And the goal here is to invite you and everyone here to help guide development, because it could go in many different directions. I'm particularly grateful to Tehanga for hosting us while we're here, and the EPA for allowing Doug to host us while we're here and set all of these meetings up and opportunities for community involvement in the research. So particular thanks to Doug, and also to our Maori collaborators who partnered with us from our first visit, that being Doug, Aroha, Mel, Jan, Ocean, who is here, Maui, and Thomas. The reason why we are in partnership with them is because any proposal to alter the environment of Aotearoa, even if it's intended to benefit the Taonga, must be consistent with Maori values. And we seek Maori co-governance over any proposals to use those technologies for which our group is responsible in Aotearoa. If Maori, who of course have a tremendous diversity of views, but if there is not broad support within those diverse Maori communities for a particular proposal, then our group will have no part of it. That's what co-governance means. That's in part because, of course, the treaty guarantees Maori rangatira over the Taonga species. So legally speaking, I would say it's there, but I'm an outsider and I'm not a lawyer either, so what do I know? More importantly, I would say, yes, as a scientist, as someone who is trained in traditional reductionist thinking, that Pukapuka is uniquely adapted to understand the local ecosystems here. That is to say, even if you don't share the Maori value system, then you should still take their concerns based on that value system very, very seriously. And you should do so even if those concerns cannot be translated into the reductionist language of science. And that's because, bluntly, we are very, very good at understanding the causal relationships between two things. Because we isolate everything, simplify the rest of the system down to that particular interaction, and we study it, and that works very well. That does not help us understand a complex system of many interrelated parts. It does give us power, because it allows us to understand that particular interaction and then arrange it, and then that can have an effect on the complex system. It doesn't really help us understand the response to that entire system. In contrast, if you have grown up living in a particular complex system and observing it, your intuition has an understanding of that entire system in a way that is not accessible to the logical part of your mind. So Dan Kahneman, who's a Nobel laureate and cognitive psychologist and economist, would say that he describes it as system one, which is your sort of intuitive thinking, can encapsulate the entire system and gives you your instinctive knowledge of it. Whereas system two is your logical mind. And system one has about 100 times the processing power of system two. So your system one might understand something. So that's why all of you who have grown up here may understand something about the environment that a PhD ecologist might not, if they haven't been exposed to it in the same way that you have. Similarly, as someone who studies evolution, in both its cultural forms as well as biological forms, a system of values that has evolved in the context of a particular environment has evolved adaptations to that environment. So I would not at all be surprised if the Mataranga Maori has something useful to contribute in terms of whether or not this moves forwards, speaking in purely empirical terms of likely outcomes. We just will not be able to understand those in reductionist terms unless we study it for several decades, which is too long. Now, part of taking responsibility for your actions means standing up in public and admitting when you were terribly, terribly wrong. So, in trying to remedy a past such error, I committed another one. And that is why it is a sign of the tremendous generosity of my Maori partners. They are still willing to invite me here to speak to you today, because I failed them. Neil and I, who is here today, we published a paper on the use of these technologies for conservation in general, but we used Aotearoa as an example. And while we ran it by some people from Predator Free 2050 before publication, I thoughtlessly just did not consider sending it to our Maori partners. And that was entirely my thoughtlessness. And it had repercussions because that paper raised some hackles around here in some quarters, political repercussions. And as Mel said in response, speaking of me, his naivete of the political situation Maori are in, and the publication of this paper without talking to the other partner, more than likely will have consequences for that partner, Maori, that the author did not consider. And her words are searing and they are true. I failed in that regard because I did not take into account the fact that there might be repercussions on the local political ecosystem that I did not understand. And that is an example both of how it is important to take responsibility in public and use your failure as resolve to do better in the future and remind yourself, but also of the importance of consulting with locals who do understand those local factors, those local systems, before you act in a way that will perturb those systems, because they know things that you do not. So, the goals of this project, if there is to be a project, number one, is to protect the native species and ecosystems. One might say, in service to Maori, or in response to the Kaitiaki Tanga, by painlessly removing invasive species. Now, particularly I am concerned by the painless part, because I'm very concerned with animal well-being. And poisons are not very humane. They cause a great deal of suffering. It would be better if we could control these species without causing any suffering. But goal two is sort of a meta goal. It is to set an example of how technology development should proceed, which I believe needs to be, in most cases, in the open, especially if it's about ecological engineering, and inviting the advice and guidance of the people who might be affected from the earliest stages, and especially if there is an indigenous community in the area, inviting their input for the reasons that I described. Now, if we're going to do something about an invasive species, then, and we're going to use biology, well, we have to face up to the fact that we invent almost nothing in biotechnology. Instead, we look at what nature has invented, and we co-opt. So even CRISPR genome editing, which now we all use, is a tool that, of course, nature created, and we simply learned how to use it for our own purposes. Similarly, there are natural systems that can reduce the fitness of a population, that is, its ability to continue to reproduce. So one example of this that's very common is genetic conflict. You can imagine some genes that might provide a large benefit to one sex, but might be costly to the other sex. And if the benefit exceeds the cost, they can spread And that means you might end up with, say, males that are very high fitness and females that are nearly sterile. So this actually does occur in nature. There are also some genetic elements that manage to spread even though they don't offer a net benefit to the organism that carries them. These are called gene drive systems, and they spread by distorting inheritance in their favor. So an organism might reproduce fewer times, but there's a greater chance that the offspring that are produced will inherit these genetic elements, and so they can spread even if they reduce the organism's fitness. And these are mosquitoes now because there are Aedes mosquitoes in Indonesia that have what's called a meiotic drive that is linked to the sex-determining element. So anything that inherits it is male, and it distorts inheritance in its favor. So the populations skew male. And if you introduce one of these into a population of mosquitoes that hasn't seen it before, it converts them all into males and the population vanishes. This might even have happened on a larger scale. That is, species may well have gone extinct in the past because of this. It's very possible. We would never know because the odds of it happening while we're here to watch are so small, given that all of human history is an evolutionary hybrid. But theoretically, it has likely happened, given how long that evolutionary history is. That is, genetic level elements that can spread, even though they harm fitness, may well have completely removed entire species. And we know it can work for local populations. So the question then is, can we harness this same method that appears in nature and apply it to these invasive species? So one way to do this, which we first described a few years ago, is to use CRISPR, which again is our molecular scalpel that we can use for genome editing. CRISPR lets us target and cut just about any DNA sequence in any organism throughout the kingdoms of life. If you can cut it, then you can edit it. But what's different about this particular form, which creates a gene drive, is we don't insert just the change we want to make. We encode next to that new DNA sequence the CRISPR system and the instructions for making that change. That is, you teach the genome to do genome editing on its own. So put this into the reproductive cells of an organism. CRISPR will cut the target site in the genome where you want it to be inserted, and it will copy itself in. Now this cell knows how to do genome editing on its own. It will continue to produce the CRISPR system, which will cut the other chromosome, copy itself over. So now you have two copies, which means that when this organism mates with a wild-type organism, all of the offspring are guaranteed to inherit. And in those offspring, genome editing happens again. CRISPR cuts the original version and copies over the new one, meaning the next generation is guaranteed to inherit. And editing happens again, and again, and again, and again. So what we've done is by encoding the instructions to do the editing in the genome with the edit, we've duplicated a gene drive. And in fact, there are natural gene drive systems that work exactly like this in numerous organisms throughout the kingdoms of life. Now, in that original paper, we had suggested that this kind of technology might be broadly useful for a wide variety of potential applications. And you'll note on there is a prominent picture of a rat. And we suggested controlling invasive species and sustainable pest management on there. But putting that figure up there like that was a mistake. And there were a lot of caveats in that paper, in the text, and in the supplementary material. But when you read a paper, do you read the text in detail? How often do you actually read the supplement? Especially when the paper is 40 pages long, as that one is, because it was strove to be completely comprehensive as to everything that technology could possibly do. You don't. So the takeaway that people got from this was that this technology can be used for all of this stuff. The reasons why it shouldn't be have to do with invasiveness. That is, the problem for this particular application is that these are invasive species. But if you're building something that is itself invasive to counter them, well, the thing about invasive species is there's a native population somewhere. And since they invaded, in this case rats, they're particularly good at stowing away, our models suggest that this kind of gene drive system that is self-propagating takes only a very, very few organisms introduced in a population for it to take off. So when we modeled the weakest reported CRISPR-based gene drive system to date, because yes, it does work in a number of different organisms, this is a drive system that creates the seeds of its own downfall, because it's only copied half the time. And when it's not copied, it creates a resistant mutation that can't be cut. And that resistant mutation is not nearly as costly as the drive system. So natural selection favors the resistance mutation over and above the drive system. So the drive never gets above 40% frequency in the population. But when we modeled it, we found that it only takes 2 organisms before you have a pretty significant chance that it will reach that maximum frequency of nearly 40%. And by the time you release 10, it's almost guaranteed down. 10 organisms introduced into a population is not very big. And rat gene flow on ships is very likely to be enough. Even if it's not enough, there are many people who know much more about rat biology than I do who think that invasion is not quite that easy. Very well. But what about, keep in mind that this is a very weak drive system. If you plot the frequency of copying against the migration rate required for likelihood of invasion, well, any drive system we actually would use is going to be nearly 100% efficient. So like the current versions in malarial mosquitoes are 98% efficient. And those things have a near unity probability of invasion, out to 1 in 100,000 individuals being moved. It's actually out to 1 in several tens of millions. So that says that the real ones are going to be more invasive because they're not going to be vulnerable to resistance. But even if it still wouldn't invade on its own, people will move them. And that is very clear given a local example, that of calicivirus. Now, calicivirus has nothing whatsoever to do with Game of Thrones. Rather, it is the cause of rabbit hemorrhagic disease. And it's a great example because Australia tested it on Warding Island, same place where they had tested the earlier myxomatosis virus that worked for rabbit control. Unlike myxomatosis, this one escaped their island field trial, moved to the mainland because it spread by blowflies, which was not known at the time. And it was not known that blowflies could move between the island and the mainland, but apparently they can. So it escaped and began spreading in Australia, possibly assisted by people. But what is known is that New Zealand decided that introduction should be illegal because it was not adequately tested. And a group of New Zealand farmers smuggled it in anyway. Because rabbits were causing damage to their fields. The total economic damage caused by rabbits has been estimated to range between $7 and $15 million a year. For comparison, the total economic damage caused by rats at the same time in the United States alone has been estimated at $20 billion per year. So what are the odds that someone will move a suppression drive in rats were it to be proposed for use anywhere? I would say, given human economic motives and incentives in response to them, the odds are 100%. That's just how people act. So this was why we wrote this paper. It was because we were very concerned that it would spread. But in our eagerness to correct my earlier mistake, we wronged our Maori colleagues because we were moving too hastily. And that's just an example of why we need to be careful and invite opinions from many different people who know more about the relevant systems. We have to be careful because the power of technology is increasing. So, if you can't have a version that copies itself indefinitely, how can we confine it to a particular population? And the best answer that we've come up with to date is to say, okay, the problem with this version is it has everything it needs to copy itself in one place. So let's separate them out. Let's scatter these CRISPR components throughout the genome and relate them in a daisy chain. So element C has the instructions telling CRISPR to cut element B and copy it. B has the instructions telling it to cut element A and copy over A. So C causes B to be copied, B causes A to be copied. There's nothing causing C to be copied. C is a normal engineered gene. And as Charles Darwin said, man selects for his own good, nature for that of the being which she tends. Which is a way of saying, when we alter an organism, whether by selective breeding, as in Darwin's day, or
CRISPR nowadays, we're doing so for our benefit. We're diverting its resources towards whatever we want it to do, in this case, copy something, and away from replicating it. And that means natural selection acts against it. There is no known example of a human-edited organism that is more fit than the wild type in its ancestral habitat. Not one to date. Doesn't mean it's impossible. I think it's very, very possible. But it's unlikely. And furthermore, we can engineer these so that they are particularly costly. So the point is, engineered genes normally go one direction in the environment. Yeah. But if you have one organism that has this CBA, as it mates with wild types, and C isn't copied, eventually you're going to get organisms that don't inherit C. So if you have a CBA organism that has two copies of each, then 2 generations later you get the first offspring that has lost the C element. One more generation of mating with wild type, and you get an organism that has lost the B element. It just has A. One more generation, you get the first descendant that has not inherited any component of this daisy drive system. And of course, if natural selection is removing all of these, then the net effect is a temporary amplification of that A element that then eventually is removed because it runs out of C and then B starts going down. It runs out of B and then A starts going down. And that's, in this case, that's what we want, because we want to not have to release that many rats into the environment, right? Rats are the problem. We don't want to release a lot more of them in order to eventually get rid of them. We want to be able to release as few as possible, have the genes amplified over rat generations, remove the population, and then be gone. No more engineered genes left. So this is one possible way of doing it, and I think this is sort of the basal or foundational way of doing it. There's lots of different ways one can go from here. In fact, the nice thing about this is that, of course, it's a daisy chain. So you can think of every link in that daisy chain as being like genetic fuel, meaning the more links you add, the more powerful it is, because the longer it goes before it runs out. So you can tune the power of it. But that's not the only way to do it. Instead of having a daisy chain, imagine you just have many D elements, lots of them throughout the genome. They all independently assort, so they're all inherited at random. But they all ensure that A gets copied while at least one of them is around. But after one generation, you lose half of them. 2 generations, you lose the next half, the remainder, until eventually they're all gone. So again, this is a temporary amplification effect that then runs out. It's just a different way of doing it. So we call this a daisy field. And either daisy chain or daisy field can get you quite a lot of amplification. So you don't want to wait too long, because the goal is to get rid of these species. You don't want to wait more than a decade or two. But in 20 rat generations, you can get 500-fold amplification. So only have to release 1 rat for every 500 rats that are currently out there. And that's assuming you're doing a one-time release. You might want to release, say, 1% every year, and they happens faster. So how would it work? Well, recall that nature sometimes does this by distorting the population in favor of one sex. And that's one way to reduce it. Another way to do it is to have spread an element that favors one sex at the expense of another. So here's an example where you have a daisy drive, a daisy chain drive, that only has 2 daisy elements left at the top. So if you track it all the way to the right, you see that there are some descendants that won't inherit. So that's why it is ultimately temporary and transient. But here on the bottom left, you see that 2 carriers have mated. And so these organisms inherited a drive copy from both parents. And what the A element does in this case is it disrupts a female fertility gene that is recessive. In other words, you only need 1 copy for females to be fertile. Which means, as long as the drive system is spreading and always mating the wild type, all of the offspring who are carriers will inherit 1 functional copy and will be fine. It's only when you get a lot of copies in the environment that they start mating with each other, and then the female progeny are infertile. So the net effect is that the drive system spreads and becomes common, and then it crashes the population because all the females become infertile. So that's one possible way this might be done. And we're currently developing this. Our collaborators are working on it in mosquitoes. for human health applications, although there may also be conservation applications of life. And we are developing it in worms in order to study evolutionary stability. But we believe that reversibility is very important in this case. But there's two different kinds of reversibility. You might say there's active and passive reversibility. Passive reversibility is ideal because if this works, the goal is to have no more rats, meaning no more engineered genes in the environment. But what if it fails? We have to take into account the possibility that no matter how well we design and model and test, maybe this will fail. In which case, ideally, we want all of the engineered genes to go away on their own from the rat population, even if there still is a rat population, just in case. The other safeguard is active. That is, supposing either we screw up, but more likely someone else does something unauthorized, we want to ensure that it's possible to remove all engineered genes from the population, from any population, no matter what. So Ashton, you're another student in the lab, is working on being able to do this and show that it works in those populations of worms. And the goal is to ensure that no matter what anyone does to a wild population, it's just like graffiti. We can wash it off, and the species will be like it as it was before. And I think that's important, even though I don't particularly value the natural world being exactly as it was before humanity was ever around. Many people do, and we should respect it. Now, how do you go about doing this? How do you ensure that things go away on their own? And another wonderful trick that nature has shown us is how to pair genes so that their fitness depends on how many copies there are. So you might have heard of hybrid vigor in crops in particular. So the vast majority of our crops, whether they're conventional or GM or organic or whatever, almost all of them have two separate parental strains that are grown up in seed farms. And then those are crossed to generate the seed that farmers actually grow en masse. And that's because having one copy of each gene for a bunch of different loci gives you better fitness effects. But it's also possible to have two different versions of the gene that do the opposite. That is, you have one of each, and you're very unfit. So if you have that sort of situation, the wild type is one version, and you spread another version where it's bad to be a hybrid, then you can imagine if your engineered gene is rare when the daisy elements run out, most available mates will be wild type. And that means all of the offspring will be hybrids. And if most of your offspring are hybrids that are unfit, the natural selection is acting against you, and quite strongly. Whereas, if you end up in the majority, the natural selection will favor you because most of your mates are your own kind. If the other allele that is penalized. So what this is a way to let the genes vote, in a sense. That is, they can sense the other genes in the population because they're constantly mating with them and being exchanged. So whichever is in the majority wins. So if we arrange for this setup to be the case for all engineered genes, then we can ensure that no matter what happens, as long as they're in the minority, natural selection will ruthlessly crush them. And this is very important because we only want them to win in the area where we want whatever the effect is to happen. Even if it's two cities right next to each other. If one city wants something and the other one doesn't, we want to be able to edit the population such that it's stable in that area. But if any engineered genes cross the border, natural selection eliminates them. And this sort of thing would let us do that. It would also, in this case, ensure that if anyone moved rats off of Aotearoa to other places, or they stowed away on their own, then natural selection would eliminate them because wherever they went, they would be in the minority, and therefore selecting. So this is our additional safeguard. There's lots of different ways that one can do this. But that overall plan is the direction we're interested in going. And again, we haven't yet built these in any rodent. The Boris project is the first for that. And those are in the mice. Rats would only follow once we know that works. And development could proceed in many, many different directions. So the question is, what should we do? Which direction should we go? Is daisy chain better? Is daisy field better? We don't know how feasible field is. That's going to come a little bit later. Do you need the threshold? What kind of threshold? Would you prefer male biasing? Would you prefer female fertility? Would you prefer male fertility or female biasing? Or combinations thereof? What is most important? What are we not thinking of? What are we missing? What might go wrong? So, there's a lot of questions that you might be asking. This is just some of them that we thought of that you might want to consider. And they're roughly in order of importance for consideration. Because the first one is this something you're even remotely interested in at all? That is this, and the question is not, would you support doing this? Because there is no this at the end. The question is it worth continuing this conversation? Is it worth continuing to evaluate whether this is a good idea? And if so, if it is worth continuing this conversation, and you're deciding to guide our research in which you decide what we do and we are the technical hands to make it happen, then what is the best way for that to happen? Because no one has ever done this before. I mean, we have a project in Massachusetts working with some islands called Mice Against Ticks, where we're similarly doing a community-guided model. But those are islands with 10,000 people. That's a very different scale of community involvement and guidance. That also doesn't involve any form of gene drive at all. It's just very simple engineered genes. But one of their requirements is they didn't want any foreign DNA. And we said, okay. Now, your view on the importance of foreign DNA might vary. What is foreign? If we ask the biologists in this room to agree on what a species is, I bet money we couldn't. Because there's tremendous dissent over what exactly is a species. More to the point, raise your hand if you've eaten beef today, or in the last week, say. Yeah, a lot of people. Did you know that cows are 25% snake? By DNA content, it's true. Because less than 1 million years ago, a tick bit a snake, got infected by a virus that was in the snake, and a snake gene that has one of these jumping genes, which is a form of gene drive, by the way, which is why they're so ubiquitous, jumped into the virus, which got into the tick. The tick then bit a cow, the virus got into the reproductive cells of the cow, and the snake gene jumped out. And the cow genome had no defenses preventing it from jumping, so it jumped until it was a quarter of the cow genome. So this is just evidence that you don't think cows and snakes are all that close, and yet they share a whole lot of DNA content. And this happens over and over again. So our standard notion of a species as being something that is separate and not related is actually, on the DNA level, it's wrong. And interestingly enough, if you look at the DNA view, that tends to support the view more analogous to that of Pukapuka. That is, organisms are related insofar as they interact with one another. Because the more closer they are interacting, then the more chances they've had of exchanging DNA. So, according to that view, the wish of the islands of Nantucket and Martha's Vineyard that we not use any foreign DNA, well, what does that mean? Foreign in what sense? They said, well, we would prefer that anyway. I explained the snake cow thing to them, and they said, oh, and that was eye-opening. But we'd still prefer it to be not. And we said, okay, because it's their environment, it is their call, we will do whatever they tell us to, they are in charge, not us. And that's the way it has to be here as well. It doesn't matter why you don't like something. The point is you don't like it, and so we won't do it. Now, so that's the origin of this, should all genes used be found within the animal to be altered. In this case, it's a little bit more complicated, because if you were to say, no, all genes used must be from the rat's mammalian cells, then we can't do that, because we need CRISPR. But if you say all genes must be from the rat, well, I can do that. Because if I take a dead rat and I put it in a blender, and I do a DNA extraction, I will get all the CRISPR genes I want. And in fact, the ones we're developing are specifically those that you could find by doing the rat in a blender experiment. So all the DNA we're using, we'll be able to make all of these for mice and rats is using DNA that you can get from a mice or a rat if you put it in a blender that way. But if you're a die-hard no, species are species, and regardless of how much DNA they share or move around and so on, then you're going to say that's not acceptable because even though it all came from a rat, some of it came from the microbes in the rat's gut. Although, in response to that, you might say, well, we're not so separate from our microbes, because after all, the rat doesn't work without the microbes. The microbes don't work without the mammalian cells of the rat. And a couple weeks ago, the stock of all the CRISPR companies tanked because a report came out showing that humans have antibodies to the most common CRISPR protein used for genome editing. Because that one comes from the bacterium that gives you strep throat. So most of you probably have antibodies to it. Not because the bacteria really got in your bloodstream, because it didn't, and you would have had sepsis and you might have died. No, it's just because the boundaries between our cells and those of the microbes are a little bit permeable. So their proteins and DNA get into our systems all the time. So who's to say what is connected and is not? I don't know, but if you're unhappy with it, then say no. So finally, are particular types of natural population suppression worthy of emulation? Do some make you more comfortable than others? It's very early days, we can do all sorts of different directions. And lastly, the one I am least well equipped to even suggest avenues of approach. What do you need to know about the ecosystem and the rat's role in it in order to make decisions in this area? This is, again, the very, very early stages. So there's a lot of time to work this out, but we would appreciate guidance as to which directions we should develop this in. Because some may well be better than others, and in ways that you might notice and we might not. So, particular thanks to all of our collaborators on our DAISY-related projects, responsive science in general, and our other projects, and particularly on DAISY Drive Aotearoa. People in my group are in bold here, and Ashton is there, who we're going to take off of the airport. Thanks to Neil and Dan, our scientific collaborators, locally on that one. And again, Haringa and Doug, Aroha, Ocean, Mel, Jan, Maui, and Thomas. Thanks to our funders. Full disclosure, yes, we are funded by the US military. See the DARPA right there. If you're concerned by that, let me tell you, one of the really annoying things about working with DARPA and the US military is they have this idea that research should result in milestones and deliverables. Biology doesn't really work like that, but they still insist on it anyway. So they insisted this detail of statement of work, you will run these experiments and you will produce these successes by these dates. So I insisted that if we were going to take their money, then that everything needed to be done in the open, and they said fine. In fact, they're requiring greater openness, so everyone they fund do gene drive related work than any other funder. So that's a weird world we live in. The US military is the most concerned with the ethics of openness in research. But anyway, ours is completely open, so you can see exactly what DARPA has asked us to do. And that is all we are doing with those funds, because otherwise they will prosecute us. We also are very grateful to our other funders who are not quite so stringent about time constraints to what we can and cannot do. But for all of those as well, all of our grant proposals that we wrote asking for money, the details are available online. And our specific experiments involving gene drive, we always put up manuscripts, preprints, not peer reviewed, that just detail what we are doing and why. And we invite everyone to take a look at it and try to find out if something goes wrong. And I do this because I myself am designing new kinds of drive systems that were not intended to spread indefinitely, have more than once come back a week or two later after initially doing a design that I thought was promising and found, whoops, nope, that one's self-propagating after all. So I don't trust myself, which also, no offense to people like Neil, means I don't trust any of my colleagues to work out stuff on their own either. I think everybody should be open about what they're doing and invite others to catch mistakes. Because nobody's expert enough in enough disciplines to figure out everything that might go wrong. We are only wise together. And finally, I should just emphasize that while it might seem that I'm doing something courageous here, coming and talking to you, and pioneering this new method, I'm at the MIT Media Lab. My likelihood of getting tenure requires me to do controversial things that get in the news and generally cause a ruckus by challenging the system and trying to make it better. So I'm just following my incentives like most people do. The true heroes of this story are the people in my lab, especially my students, who really are putting their careers at risk. Because the reason why most research is closeted is if you share your brilliant idea and someone else gets it working first, they get all the credit and you get none. So it's my students that are the real heroes who are putting their careers on the line and doing what's right. So thank you very much. I'm very happy to take questions and answers.
So we're just going to open the floor. So any questions, fire away, and I'll try and manage them. Right after that. Here we go, David.
I was trying to formulate my question, but about what you said about talking to people and making sure that you address, if someone's unhappy and uncomfortable about something in your experiment, you should stop it. But I mean, we live in a world where there's a lot of irrational thinking. So where do you put the limit where an opinion is worth considering and not? I mean, is you must be confronted all the time by people that say, well, you're talking about evolution, but that's not a thing. So how do you handle that? How do you handle irrational people, and where do you put that limit?
It's a great question, and it's one that we have not yet really had to deal with, because it turns out that people who don't believe in evolution tend not to show up at lectures by someone who needs a sculpting evolution. So,
Well, yes.
but to be fair, it does happen, in the sense that there are people who come who are. So at our very first meeting for Mice Against Ticks on the island of Nantucket, we had a town hall meeting, the Board of Health of the island hosting us, and it was advertised, so about 30 local citizens came, and one of them, who is an herbalist, she was just hopping mad at the very suggestion that scientists might genetically engineer the environment and just make things worse. But she ended up, after hearing a lot about how we wanted her to share all of her suggestions and concerns, and in fact invite everybody else to do the same, and that we wouldn't do anything the community didn't want, she thought about it and said, I really want to see where you go with this, because even though I personally suspect it's going to be a bad idea, if I oppose doing science this way, then I guess I have to say that I'm anti-science. And I don't think I'm anti-science. I just want science to be done in a way that I think is open and gives people a voice. So she is now on the steering committee of Nantucket. And she objects to what we're proposing to do frequently. And that's good, because we listen and we talk about it. And she makes a point of going to the community and inviting anyone who has an objection to share it with her, promising to bring it up on the steering committee. And that ensures that anyone who might have an objection, that it is heard. But we obviously can't promise to heed every objection and derail the project and go in a different direction, because people do want different things. There we've been very lucky that most residents want the same thing. Namely, there's about 3/4 of them decided they didn't want foreign DNA no matter what's in cows. And so that's what we're doing, because that's a very clear divide. Now, it was an educational divide. I mean, 25% that said, no, go ahead, it will make it better, use foreign or synthetic DNA, were overwhelmingly the ones that had some kind of technical education. But they got outvoted. That's how government works. So we're not using foreign DNA. And similarly, it would have to be the same sort of thing here. Where you draw the line is sort of unclear, but it's going to be especially hard here because we do believe that if there are going to be objections from, in particular, Maori that cannot be translated in terms we can understand, again, I think those are going to be important. So it's going to be a question of what fraction of the Maori community agrees with that objection. And if it's a substantial fraction, then that could very well be a don't go that way. But if it's a comparatively small minority, then that's probably an overall decision-making process that would best take place within the Maori community. It's not our place to tell you which direction you want to go. The whole point is you tell us what you want, work it out according to whatever civic governance mechanisms you think are appropriate, and tell us what to do. I don't have any better way to go than that. It may be that this will slow down the progress of science and technology if we do it this way. there's also quite the acceleration bonus, I suspect, just from doing everything in the open, because right now the system is so ridiculously unbelievably inefficient, incentivizing everyone to keep things a secret. When we know that most progress comes from sharing ideas and improvements and synergies between different concepts, and now we have to wait the 1 to 2 year interval before projects get completed and published for that. So I bet the acceleration from making science open would more than compensate for any slowdown in applications. And frankly, don't you want to slow down for applications for things that might be dangerous? I mean, the whole point of this is to ensure that technology is developed in a direction that is more likely to do good in the world and less likely to do harm. And that does mean slowing down avenues that might be at greater risk of causing harm by whatever criteria. And I'm willing to accept that, because I don't want things that I hold myself responsible for to be used unwisely. And if that means that in some cases they're not used, when in fact it would have been a good idea, certainly given prevailing opinions of biotechnology, it's better to err on the side of caution. Because anything going wrong, the social impact would certainly be greater than the ecological. So I would rather be told no and walk away.
You spoke a little on the ecological consequences of such things. I'm curious to know if you and your team looked at trophic estates, as a New Zealand example, how rats and mice are mesopredators and got other bigger things that if they're not preying upon them, they could easily jump and actually exacerbate the situation even further. So have you written models or simulations and that kind of stuff?
We haven't done anything in the context of New Zealand, no. And that's very much something for local ecologists to look at. And again, this is the technology, I mean, it's CRISPR-based, right? It will work in pretty much anything, in all likelihood. Plants might be a little difficult because it seems like they don't copy DNA nearly as effectively. But even there, I think people just haven't expressed it at the right time. Someone could do it in mice and Radistratus and Radiculatus, and the stoats, and the ferrets, and the possums, and so on. But some of those are going to be available first, so maybe, based on your point, you should try it. Until you hit all of them at once. Maybe that's going to be necessary. I don't know. My rules for engineering complex systems is make the smallest possible change that you think might solve the problem. And always start small and local and see what happens before you scale up. So in that case, try it in a small area and see what happens maybe. Maybe you take out the rats and then the stoats explode and cause even more damage. So at least you were able to try it in a very small area. And then you stop. And know that you have to wait until you control the stoats as well. But again, I am not an ecologist, so I should defer to those who are.
A couple of questions relating to artificial intelligence and nanotechnology.
Okay.
I've not heard of them following your openness approach and willingness to wait. And yet they also, to me, with genetic modification, pose huge threats. And so I wonder if you're doing anything to influence those seeds.
Well, that is a small component of my grander scheme. But admittedly, I am most focused on the risk that we might discover something truly dangerous, not seeing it coming. Because this very technology of self-propagating CRISPR-based gene drive, we thought of it first. We publicly described it. We tried to raise awareness, particularly among people who might independently invent it, not realizing it might take off in the wild. And we failed. The group in fruit flies independently invented it without realizing it might spread in the wild because they were developmental biologists. They had never heard of a gene drive. They didn't think about evolutionary effects and fitness or anything like that. They wanted a way of knocking out both genes in a single step and making it easy to maintain their fly lines in the lab. And they developed it entirely around that. And it got published even though the editors should have known better because they had seen our work, and the reviewers should have known better because they had seen our work. So at least we got in contact with those scientists, and they agreed to edit their paper at the last minute to include mention of safeguards, and then we got together and recommended consensus safeguards for everybody to use, and thankfully nothing got out. And that's a warning sign. It means that if there is something dangerous out there, we're going to walk right into it. So I want more openness, at least in general among research. I want people from different fields to have to scrutinize different proposed research before it gets done to identify stuff like that. Because the next thing might be more dangerous than this. Nanotechnology, again, these are out of my field, but I do sort of specialize in global catastrophic risk. It's one of the things that I'm deeply paranoid about. Nanotechnology I'm not terribly worried about because biotechnology is nanotechnology. We have to get very, very, very good at nanotechnology to design something that is better than existing living things at utilizing resources in cell property. Gene drive is the first thing where we can even edit something that does already live and exist. Everything else is natural selection wipes it out. So I'm not worried about breakthrough scenarios or anything like that. Artificial intelligence scares the Jesus out of it. Because yes, artificial general intelligence is one of the things that could destroy us all if we get that wrong. And there are issues like OpenAI, but then there's the question of, do we really want it to be open? Because is that really the best strategy for that sort of thing? I mean, do we want research on dangerous pandemic viruses to be open, or do we want to just not do that? Openness isn't always the right answer, which is why I'm not even sure I would say I want all of science to be pre-registered. I definitely want it to be pre-registered and distributed to a select group of experts in diverse fields to identify dangerous things like you are working on. And I think the best way of doing that is changing the incentives for one field, gene drug research, and setting an example of how environmental research in general at best be open, but only in fields where we're reasonably certain don't pose that kind of threat. So yes, you're getting at my larger scheme of trying to use this as a lever to change how science is done in order to reduce that kind of threat. But I don't have any good answers for that. Sorry. We'll still working on it.
Great talk, Kevin. Thank you for that. I really appreciate it. In your phosphologgy paper, you and dear Professor Gemmell down the front there seem to discount gene drives from conservation purposes, at least regret suggesting that. Is that still your position? And secondly, you didn't talk about precision drives in your report. Are you still thinking that precision drives could be of use in this field?
Great question. So I still hold that self-propagating drives that are anticipated to spread to all populations of that species are a bad idea for conservation. You could imagine some exceptions where you might say cane toads in Australia. There isn't much of an economic incentive for anyone to move gene drive toads from Australia back to South America because the toads in South America aren't doing anything and they're not causing any problems elsewhere. But even there, how many trolls are there on the internet? How many of those people are trolls in real life? Well, less, but there's still a lot. So some people might just move it for the lulz. And
a precision drive would overcome those, or potentially could overcome those problems.
It depends on how you do it, yes. So precision drive refers to the notion of, since CRISPR is so specific, in fact so specific that it's being considered for developed actively by many, many people for gene therapy in humans. That is, we're trusting it to cut the genes we want and not your tumor suppressor genes. Then it's specific enough to not hit other sequences. But in the case of a gene drive, you will have to target multiple sequences to be evolutionarily stable to avoid that resistance problem. So you need a bunch of different sequences that are all unique to the population you want to affect. So I'm not sure that that's going to be true for many invasive species. Maybe the wasps here are different enough because that was a single point of introduction that you could get away with it. Maybe. I'm a little bit skeptical. And then the other problem is evolution. This kind of technology is really the first time that we've engineered something that we anticipate to evolve on its own, outside of our control. So what are the odds that given constant introduction exposure, that it might evolve to be able to hit that new sequence? And so we're developing worm models that will hopefully tell us that. But it's something to be wary of.
Yeah, and if I may, we weren't against the idea of gene drives and conservation. We were against the idea of self-propagating gene drives.
Yes. And but even self-propagating with cane toads. So the original strategy that I outlined in the eLife paper said use a self-propagating that spreads through the wild type, and then quickly follow with another one that spreads through the first one that can't spread through the wild type, and then use a third one that is the suppression drive to hit the second one. Then you would have to get all three kinds of toads and move them, which is probably beyond the capacity of someone doing it for the wolves. But I still wouldn't try it until we've already used gene drive against malaria. Because if there's a 1% chance that our trying something for conservation will delay application against malaria by a decade, the expected cost is 25,000 children's lives.
and I'm not willing to take that chance. So I'm not saying don't ever do it. I'm saying don't take the risk to malaria. And once that's done, then maybe we can talk. But then maybe by then, I mean, it needs to be something where there's a reason why you don't want something daisy-like or something better that we're still working on or other groups are working on inventing. So I think it's just a little bit early to say it's worth risking a self-propagating of any kind. But keep in mind that something like a daisy can readily spread something, or a threshold-dependent drive can introduce unique mutations into most populations, and that might work. So we're being, to use Neil's phrase, bold in our caution. In particular, because 25,000 children's lives is a lot to be responsible for.
So I think the conversation really is, for me, for gene drives, is what could we do that would make them more acceptable and more controllable in a global context? And Kevin's provided just a couple of ideas around daisy chain drives. But it's early days. This technology is 5 years old. Daisy chain we came up with a couple of years ago. And to me, I don't think there's enough people globally thinking about ways to harness this technology in a way that is controllable yet, because they've been focused mostly on making self-propagating drives propagate. And so actually a segue here, Kevin, is, you're talking about community guidance here. What if a community turned around and said, well, thank you very much for your ideas about daisy chain, but we want to use self-propagating drives because we think that's better than, for example, innate ability. How would that affect your worldview?
To me, that would be an example of communities continuing with the status quo. That is, doing things to solve their own problems and make their own lives better, regardless of the externalities and costs imposed on others, which has gotten us into a lot of our environmental messes. So it wouldn't surprise me. I just think it would be a bit sad if used for conservation, because most of our problems from conservation come from people trying to do other things that have externalities on other species. So continuing that same overall ideology would just be tragic. But again, I don't get to say it. If people here decide to do that, they can do that. I expect there would be severe international consequences for that. Not just in terms of delaying application of malaria, but in terms of trade and so on. So I suspect, in the long run, I think anyone advocating for doing that probably would have been shut down before they do it, just because, having talked with a lot of people at the World Economic Forum, World Trade Organization, and the like, there's too many economic consequences of being reckless in this sphere that I think the policymakers would shut it down for those reasons. But I could be wrong. And of course, it's very, very possible, unfortunately, that someone could just decide to go ahead and do it because they think it's the right thing to do. And honestly, if it's someone in Africa who has children at risk of malaria, I can't even say I blame them.
Because like species are kind of blurry, and the risk is that one organism with a gene drive could spread to a more viable population. Where is that line where a population is similar but it wouldn't be viable? So like if something had enough genetic difference or...
Great question. So CRISPR is highly specific, but variably so, in that sometimes you'll have what we call an off-target site, normally recognized as 20 base pairs. Sometimes there's 4 base pairs that are mutated and will still cut. But that almost never happens. There's 1 base pair that's off. Usually it won't, but sometimes it will. And the only real way to know, there's predictive tools, but they're not great. They help, is to test it. So generally speaking, it's not going to be similar enough unless it's a quite closely related species. That is, if you're looking at a rat, a mouse is way too far away. But other kinds of rats are not necessarily smooth or careful about your design. And then, since it's hard to predict, the only real way to do it is to test it. So the reason we're developing the worms is because we can grow them in populations of hundreds of millions to billions, and they reproduce every 3 days. Okay, go ahead.
And in the case of rats that are genetically quite similar, would you try to target ones that are unique from the kind of species, or would you just try to collect all
The way I would prefer to go, and again, this is, you tell me what you prefer, right? But I would lean towards narrow species specificity. That is, targeting Rattus norvegicus to start, because that's the ones that we actually are genotyping and have a complete genome. So they're use sites that are only found in norvegicus and not found in Rattus rattus or Rattus excellens. And then to be verified, it's not going to evolve to be able to hit those, even in the event that there were gene transfer. Then we grew up worms with the norvegicus sequence and worms with the excellent sequence, say, and worms with the drive. Throw them all together. Does it ever mutate, evolve so that it can hit the excellent sequence? If it doesn't, for a billion worms over 100 generations, it's not going to happen in the actual virus. So I would have that's up to the ages.
And you said that occasionally it does cut that top one, like usually or whatever. But like, is that like how often would that occur? Would that be in the hybrid? And it's as a danger of dealing with things in the future?
Generally, 18 base pairs is unique in the human genome, typically. So, in order to be a danger to humans, with pretty much anything we're talking about, then you need to get the CRISPR system or the DNA and the relevant guide into people, and people would need to have the target sequences, and those target sequences need to be in dangerous locations, which basically means too much pressures or similar, in order to potentially cause something dangerous. Other than that, I'm not terribly worried about CRISPR. Yeah.
So could this potentially be used for the vaccine of cancers? Because if you have two malfunctioning copies or just not, because perhaps one of the copies, could we have a system in place where if it did have a malfunction, the other one would just cut it, replace it with another solution? Would that be viable?
That is a very interesting idea that should be further studied. There are certainly people interested in using it as a treatment against cancer by targeting nucleus. I haven't heard of anyone trying to use this sort of guilty drive as an anti-cancer thing, but it's a very interesting idea. I like it.
Take it up. One more question. I'll just, quarter to 5 on a Friday afternoon. Yeah. Okay, so I think that's us for the afternoon. Almost bucky more. People taking photos, but there's juice and biscuits and all out here. Go to the shelf on your way out. Kevin's will be around to take a few more questions if you want to mail them up, but thank you very much.